Okay, so welcome everybody to PyData DC. This is our 5th monthly meetup and the last one for the year. We're really excited to have our speaker, Mike McCarthy. His official title is really big deal, really nice guy. Anyway, I just wanted to remind you guys that this event is recorded, and the people being recorded are the active speaker and anybody who's sharing their screen. So the messages in the chat are not recorded, so your interactions are ephemeral in the sense that they will not be saved after the meeting ends, and you can opt out of the recording by not sharing your screen or not being the active speaker. Another few preliminaries are the PyData Code of Conduct, which I'm going to paste in the chat. Okay, and it basically reads, be kind to others, do not insult or put down others, behave professionally. Remember that harassment and sexist, racist, or exclusionary jokes and languages are not appropriate for PyData. All communication should be appropriate for a professional audience, including people of many different backgrounds. Sexual language and imagery is not appropriate. PyData is dedicated to providing a harassment-free event experience for everyone, regardless of gender, sexual orientation, gender identity and expression, disability, physical appearance, body size, race, or religion. We do not tolerate harassment of participants in any form. And thanks for helping make this a welcoming, friendly community for everyone. If there's a violation and you would like to report it, I'm going to post the link and the instructions on how to do that into the chat now. And there you go. You'll be able to do that. Okay. So next up, we're going to have a few announcements from our sponsors, who are the people who make sure that, like this gets put on for you. We'll start with Mike and then we'll circle back to Mike. Mike, do you have any announcements you want to make on behalf of Capital One?
I do not.
Cool. Alexi, any announcements you want to make on behalf of spell.ml?
Guys, I'm Alexi. I work at Spell.ml. We're one of the sponsors of the event. We are a ML ops platform and kind of a space where you can go to deploy, train, deploy, and monitor machine learning models. I think I do actually have one interesting announcement, which is that we are currently, Spell is currently hiring a machine learning solutions engineer. So that is something that I will share in the job description for that is something that I will share in the chat.
Awesome.
Happy to be here.
Cool. Our friends at spell.ml, they're based out of New York and they're also awesome. They do machine learning, deep learning infrastructure services. Eric, do you have any announcements you want to make?
You've never asked me that before, Paolo.
Yeah, I realized that.
I was not prepared at all for this. No, I don't.
Okay, cool. And is Torian on? Does he have any announcements on behalf of NVIDIA?
I don't see him.
I don't see him. All right, he'll probably join a little bit later. NVIDIA is another one of our sponsors. Torian gave the last talk, which included a live demo and was awesome. And on behalf of MetroStar, I also don't have any announcements. We are constantly hiring for a bunch of positions. No data scientists at the moment, but a few database administrators. So if you want to go to metrostarsystems.com, check out the careers page. And if you're a database administrator and you're interested, that's a great place to go check it out. Real quick, we don't do this often because I usually forget, but does anybody, any of our attendees, you guys have an announcement you want to make, like a short one?
I'm going to jump in briefly, brother. One position we are looking for at MetroStar for data scientists is a cleared data scientist. If you have a secret or a top secret, we have some work coming up we'd love to chat with you about. So just drop that.
Great to know. Cool. All right, so I guess that's it for announcements. Now we're going to move on to the official talk. So this is Mike McCarthy. He is the Director of Software Engineering at the Capital One Center for Machine Learning, and he's going to give a talk about universal, scalable, custom estimators. Take it away, Mike.
All righty, thank you, Paula. Let's see if I can share my screen. It won't let me. Awesome. So this is a talk that Gil Forsyth and I did at GTC Fall, the virtual conference. I'm going to go through it here as well. If anybody wants to turn on their cameras, that would be totally awesome. I'll say before I start, because that way I feel like I'm talking to humans rather than just a screen. Thank you. That's awesome. Yay. Okay, cool. I'm going to get started and gonna go through a quick overview real quick. We're going to go through kind of just a quick introduction to Scikit-Learn estimators and the API. I wish we had the little, there's like, usually in Zoom, we have this little thing where you can say thumbs up or thumbs down. Maybe you guys can give me a thumbs up or thumbs down, but I'd be interested to know whether or not that is useful to you guys or not. I'm happy to skip that, but it's basically going over the Scikit-Learn API. So you can give me a thumbs up if you want me to go over that. Okay, got some thumbs up. That's enough to get me to do it. Great. So I'll do that. Then we're going to talk about kind of patterns that we've seen for adding custom functionality to the Scikit-Learn API. We're going to talk about what can go wrong in those situations and how you can get yourself into trouble. We've actually seen this in the community, and then why it's really important to get this right. We'll talk about other examples of how to extend the Scikit-Learn API in the community. It turns out that writing your own universal custom scalable ML estimators is not a new idea. This is something that's done in the ecosystem, and this talk is about how you can do that in your own work and some of the advantages of doing that. So we'll talk about that. We're going to go through a real world example of how we're applying these principles in our work. Talk about some challenges and lessons learned, and then I did do some performance improvements on the toy example that I've got here. So we'll talk about that as well. All right, more video. I like it. Thanks. All right, so quick introduction to Scikit-Learn. So if you guys look on the Scikit-Learn docs, if you've seen anything there, there are a couple of different, many different submodules in the library. Basically, what we have here is just a basic example of a linear regression, and also another method in the dataset submodule for generating data. And what this allows you to do is just kind of generate a NumPy array. You can give it certain knobs to tell it how many rows to produce, how many features, set the random state, add noise. There's all kinds of other options here, and you essentially get your target Y values and your X values out of this, and then you can use that to kind of build out your code that's completely independent of your data, and you can just think about kind of how you want to structure things, which is really, really nice. You can write unit tests and all kinds of things. So once you've created your data, whether you're using a generator or you're loading it from a CSV file or whatever, you then generally typically will perform a split of the data. You want to hold out some test data from the training data so that you can then use that test data further down in the process to kind of evaluate the model that you've created to see basically how it performs in terms of predictability and accuracy and things like that. And there are all kinds of other scoring metrics and methods within Scikit-Learn that you can use to do that. So you can kind of build up some standard ground truth around this without having to write all the math out, which is great. So anyways, after you split your data, you'll create a class for your estimator. And this is kind of the key piece that we're going to talk about throughout this talk. You then generally call fit on your training data, and you pass in your labels as well. And the model will fit to that data. Once you've created an estimator and you've called fit on it, you generally get these other attributes as well. They can vary depending upon which estimator you're looking at. So here we have a coefficient and an intercept, and you can look at those values and inspect them again to see how well your model is going to perform. And then of course you can score your estimator as well and get kind of a 0 to 1 kind of score here where you've got the score on the training data as well as the test data, and just kind of see how well the model is performing there. Also, you can visualize the data. So here we have a linear model. We can look at our data that we're fitting against. You can see it's a general scatter plot of line in a general trend, and then we just plot the line that we get. from calling our predictions, as you can see up here in the predict call. We can see it's a line. So pretty straightforward, right? Moving through that quick, but are there any questions about that? Really high level makes sense? Okay, great. So there are many different types of estimators within the Scikit-Learn API. This is a graphic from the docs that kind of help you navigate through the zoo of estimators to try to figure out which ones you might be able to use. So this is a great graphic for that, and there are tons of docs on this. So now we're going to kind of go into what is this API. You know, I was talking about this estimator thing that we had. We were calling methods on that object, and various side effects were happening, like we were fitting data and getting new attributes and stuff like that. There is actually a standard there, and I'm going to walk you through kind of at a very, very high level what that is here. So the API basically consists of four different types of objects. So an estimator is one that implements a fit method. You pass in your data and your target label, like you saw in that example previously. There's predictors. They implement a predict method or a predict proba method. And those take in new data and then give you some prediction based on that. Another type is transformers. They implement a transform method. And essentially, you know, kind of what you would think, these estimators or this method will mutate the data in some way and then return that out. And then there's a model. Those implement score methods for actually not only doing the prediction, but actually evaluating some kind of score metric on it. One quick note on terminology. We're kind of overloaded here a little bit. So on the word estimator, this is the Scikit-Learn language for estimator. We're using that generally here, even though one of those four classes is an estimator, and that specifically means something in the API. So just keep that in mind as we're going through this. So we're talking about estimators now in general, and it could be any one of these types of objects. So what do we get by following the standard? It turns out that it can go quite a long way. Estimators give us these reusable, composable blocks that we can combine in different ways. We can form ensembles, or we can form long pipelines. We can chain methods together in order to perform some machine learning operation and train some model. So quick look at pipelines. This is an example that I've taken from the Scikit-Learn docs, and we're going to kind of use it as a toy example as we go through this to try to build something that'll scale. So I'm going to pull in a principal component analysis and a logic regression estimator. I'm also going to pull in the Scikit-Learn pipeline object. I won't get into that too much here, but you'll see it. It's basically how we can compose different estimators together, depending on which four of those types that they are. And then we're going to pull in a grid search CV estimator for just performing hyperparameter tuning on our data. We're going to generate data using the datasets module, just loading digits. We're going to create our PCA estimator, as well as, so there it is there, as well as our logistic regression. We're going to initialize it with some hyperparameters. And then we're going to pull those into a pipeline object and combine them so that now on this pipeline object, we can actually execute both of these steps with one command or one method call. We'll then also initialize some hyperparameters here. And then we'll run that, we'll feed that pipeline object into our grid search for hyperparameter tuning, as well as our param grid. And we'll do the same test train split that we did before, and we'll call fit. This time, instead of calling fit on the pipeline or one of these estimators, we're calling fit on grid search CV. Again, it's implementing this API, and that's going to run this pipeline. It's going to actually run a number of fits depending on the parameter grid that I send it. And then it's based on some scoring metric going to determine which one of those models is performing the best, given the data and given the parameter grid. And so one of the things I get from this is a best score, and I also get those best parameters. When I print those out, I can see that score. I can see the best parameters that I can choose whenever I want to actually train that model for real and get it into production. And then, of course, just showing some visualizations that we can compute as well, again, to just assess the performance of the model. All right. And then also we can validate that model. We can then take those, we can actually take the best estimator that was created from that hyperparameter run, pull that estimator object out and use it if we wish. And we can even score it like we were before. Okay. Any questions about that? I know I went through that fast, but did that make sense? At a really high level, this is going to be our tour example we're going to use as we go through this.
I got a question. Your training score is 100%?
Yeah, why is that?
I don't know, man. It feels like maybe you overfit.
Yeah.
No, because Mike's really good at data science.
Okay.
Most likely we're overfit. But again, I'm scoring on the training and test data, right? So,
yeah.
All right, great. So now the question becomes, and this is kind of like the point of the customization of the estimator. How do I want to customize this, right? Generally, you're going to want to do something more than just this kind of toy example in your own code. So say maybe at some point in that pipeline, you know, we've generated data, or maybe we're loading it from a CSV. We want to mutate the data in some way before the PCA step. We kind of have two options here that we're going to walk through. One is we remove the pipeline and we just call each one of those estimators we have a reference to in that code. We can just fit on those individually and just kind of drive the API on our own. Or we can define a transformer like I talked about earlier with one of the 4 different types of estimators. We can define our own transformer that's going to mutate the data and insert it into the pipeline. So we're going to walk through those 2 examples and kind of compare the trade-offs. So option 1 is we're going to remove the pipeline and we're going to add a function that'll add features to X. And so this is what that code looks like. So here I've defined some arbitrary function. It's going to take in X and it's going to mutate it in some way. It could be calling an API, pulling in some data and merging it in. Maybe it's just removing some rows based on some criteria, all kinds of things that we could do here, right? I'm then going to create that PCA object, a logistic regression estimator as well, just like I did before, but this time I'm passing in the best parameters from my hyperparameter tuning. Say I just want to, I've already done the hyperparameter tuning. I just want to use those parameters in this. Seeing some heads nods or twitch a little bit. So let's see if they can spot the bug. So then we're going to do my test train split just like I did before. And because I'm not using that pipeline object, I've got to call fit transform on here. And this is just a convention in Scikit-Learn. It'll call fit and then transform on the data. That's just part of the transform API, but it's going to mutate the data in some way. It's going to fit and then mutate the data in some way in the PCA. And then we're going to call add features manually on those X's, and then we're going to fit on that logistic regression. And then one interesting thing to note that we have to remember here in doing this way is that whenever we want to look at our test data, we don't want to fit on it. We just want to transform on the PCA. Otherwise, you would get really weird results. So you have to think about these things, right? And then, of course, don't forget to add your features again to your test data, and then you can compute your scores, just like we did before. So how do you guys feel about this?
Don't see the bug.
Can I ask a question?
Sure.
Yeah, so this is a very dumb question, but I'm curious. So why would you fit transform the original X train and then before you add the features instead of doing it the other way? Maybe I'm missing some context here, but
why would you fit transform before adding the features? So say you just, so in this example, say you've already done your principal component analysis to figure out which features you want to use, right? And then you're just going to add some arbitrary features that you know you want to use.
Like impose a feature. Okay, I see. Thank you.
Yeah, say there's something that you know that you always want to use regardless of what PCA gives you. All right, cool. So Yeah, many times we'll use this option. Why do we do that? Generally, maybe you're new to the Scikit-Learn API. You don't want to go through all the docs and figure out which 4 of those estimators you need and when you need to implement these different methods. When you don't, you may want finer control over the code. Like what I was saying, you want to explicitly always do something at a certain point in the pipeline. You have complete control there to do all kinds of things. And then, sometimes you may share this code with others. You may package it into a library. This pattern, imagine this pattern getting copied over and over again through like out your organization, and everyone's doing this. Okay, so let's just imagine that for a moment. Why is that bad? Well, for like a one-off, if you're just trying to do some ad hoc analysis or get an answer now, it's probably just fine to do this, right? However, if you're going to collaborate with other teams, if you're going to develop a library, if you're going to tweak this and run this over and over again, maybe someone else is going to run it, or maybe your future self is going to run it 6 months from now, you're going to have to remember to not call fit on the second time on your test data and things like that. Make sure that that's right. So you can see how this kind of gets a little out of hand quickly, right? And this again is a toy example. Pretty simple. I'm sure all of you would have many more complex situations here by doing this. So, all right, fine. We're going to just share this code. So say you want to wrap this up into a class. Maybe this is what it looks like. So you have some PCA logistic regression block that you've created. You'll have it under a init that's going to take, say, a file path. And it's going to take some hyperparameters and store those as attributes for later. Maybe you have a load data function that's going to load data from a CSV file. And then remember, here's our add features function. Let's go ahead and just put that in there, right, to mutate our data. And then maybe you have a build model, or you could even call this fit if you wanted to, that just performs the code that we saw above, right? So it creates the PCA, creates a logic regression estimator, does a test train split, and remember, calls right in the right sequence all the things we want to do and not overfed our data, hopefully. And then you'd have some driver function that just runs this whole class, right? Or maybe you could make this dunder call or something. So great, I've encapsulated this custom code into a class that I can now reuse. So this is mostly fine-ish, right? But what if we want to maybe add that grid search operation back in? I don't want to just use those best parameters every time. I want to, if I'm looking at new data, I'll need to perform my hyperparameter tuning again, right? So let's write another class for doing the grid search. Hopefully people are starting to gloss over here a little bit, or maybe sweat. Can you imagine unit testing this? So we have our same vendor init method again, taking in the file path. This time, let's just go ahead and load the data on the init, right, from a CSV file. We have a run. We're going to define our hyperparameter grid. We're going to create a grid search object. We're going to do our fits, pull out the best parameters, and say we'll keep like a list of our dictionary of parameters, and we'll update that. So as we're going through here, we can kind of keep track of what's going on. This is getting really fancy now, right? Have our grid again, and then do another grid search to get that best, the ultimate best one out based on the logistic regression. So maybe we could do something like this. Okay. So now we have these two classes, right? We need to put them together. So let's define a driver method where we're going to create our custom classes, and we're going to tie them together and execute that. And this generally works, right? So there's a couple problems here that I'll point out to you. We're reading data twice. Maybe we want to read different files. Maybe we have like a validation data set versus a training data set and things like that. Or say you need to scale. You try to run this against more data, and you run into issues, right? So you can add more classes, and I'm not going to show all those classes here, but I'll add the drivers, and you can imagine we have a Dask version of the two classes and a Dask driver. We have a Rapids version and a Rapids driver, and so on. So what if we find a bug? And I hinted at this before. There was a bug in the code before. Did anybody see the bug? There's a hint. I was moving fast, so maybe you didn't see it. That's okay. There's a data leak here, essentially. All right. So if you remember, and I'll go through the code here, show it here in a minute. But when we perform grid search, we're performing on the full data to find those best parameters. However, we then have a test train split in our logistic regression, our main driver class there. So we're performing test train split here. However, we're now performing it in the hyperparameter chaining. So we've got a data leak essentially. And now that we've created all these different classes in order to scale this code using Dask and Rapids, we've got copies of this bug everywhere. And we have to remember where it's at. We've shared it with our friends and they've got the bug. We have to remember who's using this and we have to go back and fix it everywhere. And you may feel like this. All right. So option one had a lot of benefits though, right? It was reasonably fast, easy to get something done. I can crank that up pretty quickly. I don't need to learn an API, worry about mixins in the Scikit-Learn API or anything like that, or figure out what abstract methods I have to implement. But there is the maintenance burden of making changes. We saw a bug and we have to fix it everywhere. In this example, we have to fix it in 3 separate classes and make sure that that it's everywhere. So that's no fun. Yeah, and then I can't keep track of that API. Did anybody understand that API that I just showed you? I see some heads shaking. So yeah. So option 2, let's follow the Scikit-Learn API. Let's define a transformer and let's look and see what that looks like when we define that. We can modify the pipeline, add the customization, and then think about scaling. So here I'm going to bring in 2 classes from the base submodule in Scikit-Learn, base estimator and a transformer mixin. You can read about these in the docs. Also bring in our old friend ABC metadata or meta. Create our class now called add features. We're going to extend from transformer mixin and base estimator. We're going to define fit, which is going to be a no-op in this case because this is a transformer. That's kind of common in transformers, actually. The fit will be a no-op sometimes, and transform will actually perform the mutation. So that's where we have here, and this looks similar to what we had before in our toy example. So we can create that estimator now. We can create the PCA and the logistic regression estimators as we did before, and then we can insert the pipeline like we were using before, and we just add another step after PCA to add those features. And this is just using the Scikit-Learn API and the pipelines for composing them. So now I can perform a test train split, and I can actually do that on the entire pipeline. And so I don't have data leakage here and get my scores out. And it's the same overfit that we had before. So the benefits of this is we only have 1 class that we have to maintain, not 3. We don't need to write docs talking about how to make sure you're using the right file paths or calling things in the right order and that API that we made up. So fewer footguns there. And then the kind of the drawback here is I had to go read a lot of documentation in the Scikit-Learn API to figure out how to do that, right? So you have to do that. And it's a little bit harder to write. It's not, I couldn't just get that out there as fast as possible. So now let's talk about what it looks like when you want to scale. No problem. Just what we do is just look at the X's as they're coming in. You can check to see whether it's a Dask collection or a Rapids collection. And you can do a Dask and Rapids-y things in those cases. So yeah, as you kind of see as I'm walking you through this, this is actually, it's subtle, but yeah.
Mike, why are those different for Dask and Rapids? I thought those basically shared the same kind of APIs. And if that's like bank secrets, you can decide to pass.
Most of the time they do.
Yeah, okay, right.
Right.
Yeah, okay.
So maybe in many cases you can collapse these. You can say is Dask collection or a Rapids collection, right? Yeah.
Yep. Yeah, but there's that really annoying edge case where it's like, all right, well, should have had this if else. And now everything's broken in prod. Okay.
Yes, you can't get rid of these FL statements here, but at least it's all in one place, right? Your
Yeah.
pivot point is in one place rather than
Got it.
having the different classes. Yep, that's a good point. Thank you.
Just blame Tarian for this. Because he's on the
Well,
call
I
now,
mean,
so.
even in Dask, there are issues here. So like, for example, say X is a data frame. iLoc is not implemented in Dask, but it's implemented in Pandas. This is going to fall over if any of this code is making the assumptions that iLoc is available, right? And that's a Dask thing.
I see.
Distributed computing is hard.
I mean, do you also need like if it's pandas, then just do the normal thing also for, not having to set up a whole Dask cluster test harness?
Yeah.
And like, it's not like you're going to run CI on like a GPU box. So,
no.
or I mean, I'm not, but I don't work at a bank, so I don't know. I don't have infinite money.
We don't do that.
Yeah, fair enough. Okay.
Yeah.
All right, I'm done.
Yeah, so it turns out for that case, in practice, I've found that the array interface is a little more standard across all three paradigms that we're talking about here, whether it's single core computing or in-memory computing versus distributed computing with Dask versus Rapids. The array interface is a little more standard than the data frame interface. So sometimes what we'll do is we'll have an option to drop down to the array interface early in the pipeline. Maybe there's a transformer that does that. And everything downstream of that is a little less hairy. You have fewer of these checks. I learned that the hard way, so did Dan. Yeah, okay, so we covered that. So let's, again, like I said, this is not a new idea. I stole this from DaskML and QML. So let's talk about that and how this is done in the community. So DaskML is a Dask-based library that works well with the Scikit-Learn API for scaling. Here we have an example of the exact same Scikit-Learn estimators I was using before. I didn't have the import statements here, but these are Scikit-Learn versions. Remember when I was doing grid search before, turns out DaskML has a grid search that follows the Scikit-Learn API. Now I can define a parameter grid just like I did before. I can create the DaskML grid search and say that data is larger than what will fit in memory. Say it's Dask data frames or Dask arrays now instead of NumPy arrays. And it works. It just works. I've literally run this code. So that's a drop-in replacement. It turns out there's some other drop-in replacements that DaskML provides. So before I was using make regressor to generate data, DaskML datasets has a make classification generator as well. It has a make regressor method as well. And it can generate data that more data than what will fit into memory on your system. And you can create Dask arrays with it, just like you can in Scikit-Learn. And we've got the exact same estimators in Scikit-Learn that we're using before in Dask. Here, we're just going to use the Scikit-Learn pipeline. It turns out we don't need a DaskML pipeline here. But again, because we're following the API standards in DaskML, we can just throw that into the Scikit-Learn pipeline object and things will run. And I noticed the rechunking estimators in here. That's an interesting aside that I won't go into right now. However, I encourage you to try to run this code. This talk's being recorded, so you can go back and look at it. I'm happy to share it with you. It's all open source stuff, and pull out that chunk size rechunking transformer and see what happens. I'll leave that for an exercise to the viewer. All right, so let's switch over to QML and talk about how QML scales. It turns out there is a very similar make classification data in QML. We can create that to generate data on the GPU.
Hey, Mike, what's QML?
Sorry?
Oh, I just said, what's QML?
What is QML?
Yeah.
Thank you.
You're welcome.
QML is essentially the Rapids version of DaskML and Scikit-Learn. So it's a library that NVIDIA has created. It's open sourced in the Rapids ecosystem for performing machine learning operations on the GPU. It works with Dask as well, so you can operate on larger data than what will fit into your GPU. And so here I'm creating a local CUDA cluster. I'm calling make classification using QML and using the Dask submodule there. So what that's going to allow me to do is to generate more data that will fit on any one of those individual GPUs that might be on my instance. Hopefully I've got more than one, and I can strike data across them and do computations really fast and operate on more data than will fit into each individual GPU at a single time. You anything to add to that, Eric?
I mean, Tarian's on the call and he works there. So.
Oh yeah, that guy.
Yeah.
How'd I do, Tarian?
No comment, apparently.
he's eating Grubhub. Cool. So we've got similar estimators that we had before, PTA and logistic regression, this time for the QML versions. We can bring those in and add those to our pipeline and call fit on those. So, okay, what's the point, right? Hopefully everybody's getting, I'm driving this home. We have this rich ecosystem of libraries we can scale. And we always want to add some kind of customization, but we want to always think about maintenance. So how do we kind of marry these two worlds together? How do we minimize the amount of custom code that we have to maintain? Remember the nasty API that I created before. And then we want to break down our custom code into small components so that we can unit test them, like the transformer. I can unit test that. Think about how we're going to test the logistic regression block class that I created before. That was full of bugs. So we're going to follow community standards. We're going to leverage work that's already been done. We're going to extend the open source solutions. And a bonus, and I've actually seen this happen, if we follow an API and we create our own custom estimators, somebody else in another part of my organization, they don't even have to use my library. If they code to that API too, we can use our code interchangeably. And we've literally done this. That's awesome. And then, yeah, you get to find bugs in your favorite open source projects and submit pull requests upstream to make them better. That's always a good thing. All right, so kind of the design of what we're going to do in our real world example is we're going to agree on a data structure in an API. That's whether or not we're going to use NumPy arrays or the array interface or the data frame interface, and we're going to use that. But the other bonus that we get there is we're going to use that either it's a data frame API or array API as an abstraction layer between our customized logic and our data. So we start with a Pandas read CSV. We can switch over to a Dask data frame read CSV, or QDF implements read CSV. So what you kind of get here is, if I separate out the way I'm loading my data from my customized logic and I'm following this API, I can scale, right? Because the custom estimator that I'm writing, it supports these different paradigms, but it's not responsible for loading it, say, right? So it just takes input X's and Y's and performs whatever I need to do with it, right? Whether it's some custom code or whether it's just using the open source versions. I've loaded the data, whether it's in memory or whether it's on a Dask data frame or whether it's on GPUs. And as long as my algorithm, as long as my custom estimator can handle those three cases, I can run on it. So here I'm defining my own custom estimator, and I can just pass. It doesn't care it doesn't care how that data frame was created.
That's the same interface that has that like logic to go and determine, if this is Dask, do this thing. If it's Rapids, do this thing. Yep. So if you're going to write a second one of these, you're going to have that same if else logic inside of that estimator again, which scale's fine because there's two, whatever, just deal with it. Like at some point you're going to be like,
they're doing two different things, right?
Maybe, or I mean, at some point there's going to be some like scaling annoyance. Like where do you draw the line at like there's too many places in this code that has if else in this, and now you're going to write an abstraction layer across like pandas, DAS data frame, cuDF. Like, where do you have you thought through kind of that kind of downstream? Okay.
Absolutely. Yeah. And that is a pain.
Yeah.
You don't want to have those conditionals everywhere. Ideally, I don't care. So that's kind of the point here is we may have those conditionals under the fit method here. Ideally, we have as little of those as possible, and we're leaning on the data frame API or the array interface so that we don't have to think about that. And this comes back to what I was saying about if we, in my experience, I've seen that the array interface is a little bit more standard than the data frame interface. So if we standardize on that array interface, we can minimize the number of conditionals we have.
Got it.
Whenever we need to have those conditionals, though, you're absolutely right. We don't want to pepper our code with all these conditionals everywhere, right? So generally what we started to do is to build some utilities, and like the iLook problem, like a reasonable way to do that. And instead of calling iLook directly on the input data, let's use our utility method. And that way that code is in one place. There are things like that we can now start to do here, right?
Is there ever like
lean on the API or try to start to build utilities?
Yeah, like, you know, obviously these are all pretty mature projects, and contributing to new projects or contributing to mature projects like that is pretty difficult. Like, is there even a possibility of like kind of fixing the API upstream?
Yeah. Oh yeah, we've done that.
Okay.
We'll find bugs and open an issue and open a pull request.
Fair enough. Okay. Thanks, Mike.
I encourage you to do that. Please find the bugs and make this API more standard.
And Mike, quick question, man. So how much, because there's such a, I guess, myriad of different ways to handle things like distribution problems and other things. Some people might be using Spark. Some people might just be trying to do this all in Python. Like, when you're working in your team, do you guys try to sort of coalesce around a single set of things? So, okay, maybe you're contributing something that's plural, but like within your own team, you're kind of focused on a single stack. Yes,
that's right. I would not attempt to go across into the Spark ecosystem with this pattern. That's fraught with many more if statements.
Yeah.
Yeah. So that's the other thing you do is you limit. So we're just focused on these three libraries here, or these three paradigms, computing paradigms, the in-memory versions, the Dask distributed versions, and then the Rapids versions. Yeah.
How do you communicate
that? Hard enough.
No, full agreement. How do you communicate that? So especially like just thinking from an open source standpoint, you wanna say like, look, this is appropriate, like, sort of a do not, right? Like, if you're doing these things, please use this. If you're using these patterns, this is not for you. How do you like to communicate that internally and when you're sort of spitting these things up?
We build an ecosystem around a library that's doing that. So in this, this is why I have my lib here. So remember how I was talking about we want to share this code. We want to make sure it's following an API and some standards, and we can minimize the maintenance burden. So what we're doing here is by showing this as the mylib custom estimator. Mylib is our internal library. So maybe you would have your own mylib, and you're going to build a community around that library that's going to be centered around how to use these technologies and how to use this stack. And what that library then becomes is a set of examples of how to do all that stuff. And you build documentation around that, you build example notebooks, and then you build a community around that such that you start to build up an internal knowledge base, and you can kind of like level up your entire organization that way.
Makes a lot of sense. Yeah.
But you have to build it. But you're going to do it anyways. You might as well just work together.
Right. It's like your shared repo, right? Like, this is the code that everybody's coalescing on. Start here. Here's the examples. Yeah. I like that pattern.
Yeah. And you can even just start with DaskML, maybe not try to scale with Rapids right away, or maybe some of your estimators will scale with both and some of them won't, depending on the problem and whether or not that fits on the GPUs or fits into a distributed paradigm easily, right?
Yeah.
But then you have to write documentation that says that, you know, these estimators scale in this way and that way, right? So that your users then know.
Yeah, makes sense. Thanks, man.
Yeah, thank you. All right, what else was I going to talk about here? Yeah, basically what we were just talking about. Great. Okay, so yeah, so say we're going to take this custom estimator, and we were using logistic regression before, but we actually we've written it in such a way that it just takes in an estimator. In this case, it can pull in an XGBoost regressor, and then we're going to pull out our X's and Y's and call fit on that estimator object. And who knows what that custom estimator is doing? But now what we're doing is we're leveraging dependency injection to inject in any estimators following the standard API from the ecosystem. We can configure this thing to run on GPUs since it's an XGBoost regressor, or we could swap out for the Dask submodule and scale on Dask, or both. But the point is that the custom estimator object doesn't need to know about that. So
can I ask
here's an example of how to do that. Yep.
So while it may sound like, you know, like Pandas and CUDA and Dask are a lot, do they actually overlap that much? I mean, I understand Pandas because, you know, it's ubiquitous and people like it, and data frames are all over the place. But are Dask and CUDA, or like QML, are those overlapping a lot or not really?
What do you mean by overlapping? Like,
do they do the same thing? It's just a different library to do the same thing?
Torian, you want to take this?
So the APIs, we try and do the same thing. So like QML or QDF, because you're using Pandas, QDF and Pandas have API similarity. So they do the same thing to scale out. And what Dask does is it allows you to do multiple nodes of either Pandas or with Dask QDF. So that way you can scale out to, for us, multi-node or multi-GPU, and for Pandas, multi-node across the different systems. So it's just allowing you, how to say, it's like an enhancement. Dask is an enhancement that allows you to scale out to those multiple systems and build and orchestrate it and schedule it correctly.
You're getting something extra that you wouldn't have been able to do if you had only gone with Dask, or if you had only gone with QML, right?
Well, there would be Pandas and QDF, not necessarily. Dask is the enhancement, so it's like the little extra, you know, emerald spice that you throw in there to allow for this capability to happen. But there's a cost to it, of course, because if it's something that is smaller or it can only run on a single node, you're paying the orchestration and scheduling cost to do so. So you only want to do it when you're very sure that you need to scale out in that manner.
Gotcha. Thanks.
Did I do it right,
other
Mike?
words, yeah, that was great. In other words, you're relying on the API, right? So we're trusting the data frame API to be more or less compatible across these different compute paradigms. And what Torian was saying in this graphic really helps kind of illustrate the point. I wish I could pull up the specific slides in my head, but there's another version of this. So a Dask data frame is composed of multiple Pandas data frames, where each one of those data frames is a partition that is on your that your worker knows about, whether it's on one system or whether it's on a distributed system, right? What they've done with Rapids is allowed you to swap out that Pandas data frame for something called a CUDA data frame that's running on a GPU, and that partition is on a individual GPU. And I don't think you can partition across, multiple QDF partitions on multiple GPUs. Torian, is that right? You can't do that. It's one-to-one. I think so.
Sorry, say that question again. I was messing with
that. So if a Dask data frame, maybe it's not important. We'll talk about it later. We'll talk about it in happy hour.
Yeah, happy hour time. I'm good with that.
So you can swap.
I think one important thing, hey Mike. So I think one really important thing to call out about QDF versus Pandas is that it's like basically a strict subset of the Pandas API. Like there's like specific paradigms that CUDA enforces in the QDF interface to Pandas that like make it like it's not like, it's basically a subset. It's not 100% drop-in, and there's more functions in Pandas than exists in QDF.
Absolutely. Yeah. Yeah,
Just,
that's
you know,
why I'm waving my hands when I say more or
Yeah,
less, right?
totally.
And
We just let you go faster on Pandas.
And that's why this part is really important. When you're writing your custom estimator, pick what API you're going to lean on here. And if you pick data frame, you're going to run into these troubles that Eric and Torian are warning about. And that's why I say, like, generally the array interface is a little bit more complete across these different paradigms. Yeah, these are large APIs. So we've got the Scikit-Learn API, we've got the array interface, and we've got the data frame API to contend with.
And my quick question is, you talk about array versus data frame. Is there any other speed or complexity issues when you think about array versus data frame?
Speed or complexity? What do you mean by that?
Well, with using some of these libraries, is there any reason with the large distributed work that you're doing, is there any benefit to going array or data frame other than just sort of what libraries it sort of ties into a little bit?
I see what you're saying. It depends on your algorithm, what you're going to do with the data, whether or not it makes sense to operate using, like, if you have a lot of linear algebra going on, it does not make sense to use data frames and things like that. So that's one thing to consider. Another thing to consider that reminded me of is depending on whether or not you are impacted by your network at all on your cluster. You may want to analyze your DAS cluster as you're running through your custom estimator and see what's going on with your data. And you might be able to get some wins by trading off between those two, depending on what's going on there and whether or not you're network bound.
Gotcha.
Okay. Sorry, we're jumping around a little bit here. Almost done. So let's go through a real world example. Yeah. Oh, this is great. Our library that we created has this thing called safe indexing. Why would we need that, guys? So yeah, we'll walk through this a little bit. Okay, so this is our oh, right. So a little bit real world here. We're going to find our own estimator. It's derived from the base estimator class. It's going to do our customized split search CV. Say there's some reason, some alternative way we want to do splitting of our data and do our cross-code validation to find that best estimator. This is an example. I'm not going to walk through all of this code, but this is an example of how you might have written something like this and how you can put it into the Scikit-Learn API. We've got those hideous if checks here to look at our incoming data to see what type of data it is. We can put all kinds of guards in here to deal with the different APIs, whether it's array or data frame, and the issues that we're running into there as we run this. We're defining our own special cross-flow validation here. We're going to have some kind of holdout on our test train split. We're going to initialize some bookkeeping attributes. We're then going to go through our injected CV here, and we're going to split on that. That could be a Scikit-Learn CV. It could be a DaskML CV. It could be our own CV. And then we're going to call fit, find the best estimator for the split as well as the holdout. So we're going to keep track of different scores. So I'm just trying to show you like kind of a complicated example of something we can do that's close to real world that's following this API. And then we're going to like come up with our own scoring metric of how do we determine which one is the best. Here it's going to be the best holdout score, and we're going to store that as the best estimator. So boom, we've defined our own CV. So we're going to generate data using whatever we want to get our X's and Y's. Here I'm using Scikit-Learn's repeated k-fold for that CV object that I'm going to inject in, specify some parameters there. I'll use the XGBoost classifier with n-1 jobs. That's going to tell it just to use all the available cores or whatever to train. Pass in that CV and pass all that into my my init on my custom grid search here, and then I can call fit on that and get the best estimator out. And so now an example of going back to that and scaling with Dask. We're gonna create our Dask client. We're gonna create our test data, and then our, this is just that same class before, but I'm adding a couple of more of those guards here that we talked about. And then we're going to create, this is actually using Dask XGBoost. So we're going to have the same inits as we had before, except this time we're creating the Dask version of our classifier. And we just call fit on it. We can get the best estimator. Let's do a single GPU with rapids. So everything looks the same here as before, apart from this. And this is going to tell XGBoost to train on the GPU. We'll pass those objects into our custom estimator. We'll call fit, and we'll get the best estimator. Let's do a single node multi-GPU. All right, so repeated k-fold just as before, pulling in our data generator. We didn't show that here. Same repeated k-fold. The only difference here now is we're going to create, instead of using DaskML, I'm going to use XGBoost version 1 and up, which has native Dask in it. So I'm going to create that object. I'm going to tell it that I want it to use the GPUs for each one of those cores. I pass that off to my custom estimator. I then created a local CUDA cluster. I'm running this on a GPU node, say, same code. I'm just running it on a different place. Generate my data, persist just because that works well in GPU land. And then I'm going to call fit. I'm going to pass it in my client and then call fit. But the API here is consistent. Now I've just showed you
hey, Mike,
4 different scaling paradigms with the same code, just tweaked a little bit. Go ahead.
How annoying is it to tweak all of those numbers?
Which ones?
The ones on the, yeah, that, sorry, down. To go to the next slide, those like chunks and sample size, like how much do you need to like poke and prod with that to get Dask and CUDA and everything to play nicely?
Yeah, absolutely. That's part of loading your data. Remember how I said in this case, where was it? So my custom code doesn't care about how that data is loaded, right?
Mm-hmm.
So yeah, and that's normal. You're going to have to deal with that anyways in these
Mm-hmm.
in these paradigms, right? So yeah, you're right. You have to tweak that stuff. You have to know about chunking. You have to know your data. You have to understand how it's going to be loaded onto your system, whether it's in-memory system, Dask distributed CPUs, or rapids, single node, multi-node, multi-GPU.
Mm.
Yep, you have to know about all those things.
Sorry, I totally wasn't trying to like make a point. I was literally asking like
yeah,
how hard is it to like figure out, if you're doing this with Dask on CPU, but you're doing it distributed versus a local GPU. Like there's a lot of like possibilities and places that you can, just
that's
not
awesome.
know enough about the infrastructure.
It's no more harder than it is today.
Okay. As somebody who's thinking about bringing all of these tools, as somebody who's thinking about bringing all of these tools and technologies to DTN, I'm like, how painful is this going to be? Like teaching people how to like think about chunk sizes and all of this stuff, like to get optimal performance, right? Because like, oh, cool, now I have a $7 an hour GPU box, but it's not any faster. Great.
Right. Yeah, no, that's totally an issue. But the nice thing about having this library and this community that you're building is that you've got a lot of examples of how to use this custom code that you're writing. And in order to actually use that code and run those examples, those examples are also going to have to load the data. Mm-hmm. So you're still going to build that. So I mean, there's no silver bullet there. It's not going to be harder or easier than it is today. But at least you've now got a community and some documentation and some key examples on how to do these things across these different paradigms with the same code, right? Yeah. So I promised I'd show runtimes. Here's the runtime slide. So I ran this custom estimator on a P316 large. I ran it with 100,000 samples and 1,000 features. I didn't want to run it too much more because it was quick to iterate. And you can see the times here. You can actually see a difference in scaling depending on what configuration I'm running it under. And I had a couple of runs on the single on the Rapids GPU and multi-GPU. Anything stick out to anybody? Yeah, does anything stick out to anyone here at these runtimes?
Come on, y'all could see it.
So for one, Dask threaded, I got 2 runs there. It's significantly long, yeah, significantly longer in time. Why is that? Maybe running on 64 workers, single instance, threaded scheduler. So communication overhead, serialization overhead, maybe.
Yeah, that's the orchestration and scheduling that Dask has. Just trying to make sure that everyone's doing its job at time, and then reassembling as they go at the end of it all.
And
I mean, it's not just scheduling though, right? Like it's like having to serialize and deserialize crap between workers on the same node.
Yeah, it's orchestration as well. Like Dask does a lot, and it's really impressive for what it is. It's just there's a hit, there's a time hit that you take at when you do it.
We're hoping the scheduling improvements will help with that are in play right now. Actually, it's in master, so install for master and test, please. You can also see that a little bit between the GPUs here too. But the nice thing on a single GPU, I can fit all this memory onto that GPU. I'm getting pretty significant speed ups.
Quick question:
okay.
Did you is this purely Dask, or did you try UCX or any of the others?
Yeah, I'm running on AWS, so I don't have UCX, unfortunately.
You do.
You do. We should talk.
Yeah, I literally been doing benchmarks on this very machine, and yeah, it is a significant speed.
Oh, I'm sorry. You're talking within the node.
Yeah.
I got you. Yeah. This is using TCP, but yeah, you're right. We could use UCX. Yeah, that would be interesting to see. Yeah. So there's more knobs you can tweak, right? That's awesome.
More knobs.
Yay. All right. I think I'm about out of time. I'm over 7. I know some people are dropping, so I think I'll stop there. Oh yeah, by the way, how do you know whether or not you're following the API? Turns out Scikit-Learn has some estimator checks that you can run your custom estimators in, and it'll actually check that your API is implemented appropriately. So that's always good to do. Yeah, so hopefully you guys saw what we can do with the Scikit-Learn API, what can go wrong, what can go right, how to consider maintenance, how to think about scaling, how to make your own drop-in replacements and use them in conjunction with other estimators that exist in the ecosystem. Thank you guys for bearing with me there. Appreciate it. That was fun. I like all the questions.
This is good. This is really good.
Thanks so much, Mike. I'm going to let people, so obviously some of you have to go. Thanks for joining us, but we're going to be here for a while. If you have questions, jump in. People have been. Hopefully you feel comfortable jumping in with a question.
I'm going to sit down. I'm reading the comments. I love it.
Right.
I missed the beginning, sadly, Mike. I didn't get the link in time. But do you have with your estimators? Are there estimators that exist currently that you're still trying to implement, or are there? Have you seen any oddities within or differences in, the predicted results? Like,
you mean between the different paradigms?
Yeah.
Yeah, absolutely.
But
yeah.
And like I said, I missed the beginning. Like would you be, how to put this? Within all the paradigms, right? At least this is what I understand. You're also trying to figure out which paradigm would be the best one to use for your data. Is that correct?
Mm-hmm.
Okay.
And your algorithm. So like that injected estimator, you know, it turns out you guys have done a lot of awesome work with XGBoost, and it works really well in the multiple paradigms, right? Others maybe not as well. Maybe there are some numerical errors that have yet to be discovered. And because you've got, you know, you've got most of your code organized in such a way that it's relatively straightforward across the different paradigms, you can change and pivot throughout them to find these subtle differences and kind of trust that what you're swapping out is not really your code, it's the other libraries, and then come up with a MRE and open an issue.
Nice. So then you'd be able to, and this is kind of where I was going with it. So Pandas, Dask, Rapids, Dask, cuDF, Dask, cuDF with Scikit-Learn or cuML. Did you see any oddities between the four libraries, like, you know, where one would perform substantially better in one library versus the others, and are you able to map that, like with this?
When you say perform, are you talking about model accuracy or computational performance?
Accuracy.
Yeah, we haven't measured that just yet. We've measured differences, but you have to be careful because it depends on the scale of the, you know, you're changing the data, right? Whenever you're going through these different paradigms, you're usually scaling, adding more data. What you need to do is hold the data constant and then look at the difference in model performance. And that's something that you have to deliberately do, and we haven't really done that test. But that's something you could do by following this pattern.
Yeah.
Am I sharing my screen again? Can you see me? Okay.
Yeah.
One thing that's really interesting that we glossed over. All right, hang on. No, there we go. Remember the rechunking? Does anyone know what's going on there?
Oh yeah, I'm interested about that.
I need to open an issue on that. Here it is. Sorry, guys.
So wait, what is this?
Right
like,
here.
This is kind of cool.
This example?
No, your slide.
Oh, this is Rise. So you can write a notebook and then use a plugin called Rise to like turn it into slides, and you can style it and all kinds of things. And so that way you can actually, that's why I can be honest when I say I've ran all this code, because it's in a notebook. So yeah, rechunk. So I glossed over this during the talk, but in our library, our own library that we're building and maintaining, there's a rechunk estimator, and I'm going to pass that in and insert it into the pipeline between the PCA and the logistic regression step. So if you take this out, what's happening here is, so this is DaskML's PCA, and whenever you call that transform, the X that comes out is going to be chunked differently. There's a bug in DaskML. And so what rechunk does is it will rechunk the X's to match what is expected on the Y's, because that's what happens is the Y's there's a mismatch between the chunking, and fit will blow up on the logistic regression step. So you find things like that I didn't see in Scikit-Learn, and when I went to DaskML, I found it. So who would have thought that PCA would mess up the chunking? Now the answer is not to adjust to rechunk. That is not the answer, because that's going to kill your performance. It's going to shuffle data around. The real fix is to figure out why PCA is doing that in DaskML and fix it. Isn't that fun?
I thought it was. I just got out of it was like a 3-day data breaks with a pat on Azure, right? Like training. So a lot of this seemed very familiar. Can you maybe like give me like the dumbed down version of, you know, like when you said that all this serialization and deserialization was happening, was Dask doing that? So Dask is setting up your workers and it's orchestrating the job across them. I'm still struggling a little bit to understand like about whether there's overlap or not with like rapids and the GPUs. So GPUs are different types of workers for only a specific sort of task, you know, like with the big arrays, right? For the training, right? So are they really, it seems to me like they're not so duplicate, right? Like at some point the conversation kind of sounded like, oh, you've gone to all of this trouble just to make sure you can work across all these different paradigms. But it seems to me like you're not really duplicating it, right? Like Rapids is doing something different than what Dask is doing for you. And I guess I'm asking, can you help me understand what they're each doing and why they're different?
Yeah. So kind of going back to that, I wish I could pull up that graphic again. So for the data frame API and for QDF and Pandas, what Dask is allowing you to do is, in either case, is handling all the bookkeeping required to deal with out of core memory computation. You can do this just using Dask with CPUs on a single instance. And in fact, that's originally what Dask was. It was an out of core processing framework. And it turns out once you figure out out of core processing to go distributed, then at that point, you don't really care where those things that you're not worried about, the part that's out of core, you don't care if that's on disk or if that's on another system. It doesn't matter to you from that worker's perspective, right?
Yeah.
And so that's when Dask distributed, was created in order to handle that out of core processing framework across multiple machines. And that's when we introduced things like the scheduler. It becomes much more important in terms of communication between the workers and whatnot. But you can use a single core scheduler in Dask still to do out of core processing.
Okay.
So think about that for a moment, and then think about from the worker's perspective, those cores and the partition in data frame's case that worker is operating on. Imagine that partition. It's a Pandas data frame classically, right? But it could be something else as long as it supports that data frame API that Dask leverages. Could be a CUDA data frame.
Gotcha.
So there's another data frame we can invent for something else, some other exotic hardware architecture, like the M1 chip.
So
I'm not better.
Can I jump in and just comment?
Yeah.
My connection is unstable though, so I don't know if you guys will.
I guess not.
Yeah. And after George, I think you have something you want to say.
Yeah.
So
I can wait.
All right.
That may be the most ironic call out I've had in a minute. That was pretty good.
I'm gonna mute you for a second, Majid, because you froze up.
Maybe you can type it, Majid.
Ooh, I can't even mute him because his connection is unstable. That's an issue.
Mike, I have a couple of questions for you. Great session. The very last slide you showed that there's a check you can do to see if your estimator implements the Scikit-Learn API. Do you know what is the bare minimum methods you need to implement? Is it like the transformer, the fit, and those 4 that you shared with us in the beginning?
Those four that I shared, yeah, it checks that.
Okay. And you had the slides for lessons learned. I don't know if you covered it or if you skipped it, but was there anything else that you didn't share with us?
Let's see. That's a good question. I kind of got into a lot of it as we were talking, which is great. So I skipped over some of it.
No problem. Then two other questions I have for you. One is, have you used this paradigm where you do the data processing, where you have a pipeline, you do the data processing in your CPUs, but you do your model training in the GPUs, and you have them share data continually?
Sharing the data continually is the hard part there, right? Usually you have to dump to disk at some point in between those two. So you have stages, right? You have an ETL stage, a pre-processing stage, and then like a model training stage. And generally you're going to persist that model, as you know, and then you'll have a production stage and you can pull in new data, right?
So is there like architecture you can design that can keep both your CPU and your GPU busy at the during training, or do you do the pre-processing first and then you do the training separately? But that means that you're not fully utilizing both all the time.
If you have, like, if you're in the cloud, you've got plenty of hardware available, you can spin up, you're going to need to spin up multiple clusters. You're probably going to need to orchestrate something, orchestrate with something like Prefect or Airflow. I should give a Prefect talk in a couple months. That would be good. Full disclosure, I'm on the advisory board at Prefect. I have to say that. Yeah, so like then you would need something to orchestrate all that, and you probably need multiple clusters. Some of those could be CUDA clusters, some of them could be Dask clusters, and you need to think about how you want to stage that. You could keep the data in memory. One of the things that I want to try out doing, this would just be on one cluster, is using Dask's what is it? It's Dask broadcasting. So what you can do there is you can have one Dask cluster. You have multiple clients in different parts of your ETL and training pipeline. You can then use that publish mechanism in theory to have to share data. So on the Dask cluster between multiple clients. So if you follow me there, I've loaded my data onto my Dask cluster. I'm doing my pre-processing. I've finished that pre-processing step, and I've persisted the data onto my Dask cluster. I don't want to dump it to disk. I want to keep it on that cluster. I publish that data frame, which is a future in Dask. And then I can have another connection to that same scheduler, say, hey, scheduler, what are the published features that you have? Get back to handle on that future, and then do my model training in that part of the pipeline. In theory, you can do that. I've actually done the public, you can do the publish, you can share data between multiple clients there. We need to get that working in Rapids as well.
Thank you, Mike. One last question. So you shared with us some Scikit-Learn models. Do you know if Dask and Rapid support like other architectures like neural networks?
Yes. Yes, they do.
Is that on the pre-processing side or on the modeling side, the training side, or both?
I know more of the modeling side, you mean the pre-processing side better than.
So our Kaggle team called KGMon, they use Rapids for pre-processing. And then there's a quick way of sending the arrow data format to like PyTorch and others using like MXTrainer and others to just basically keep it all on GPU, maintain that speed, and then run your deep learning training or whatever other training you're looking for. And then you can come back to Rapids to validate your models using whatever decomposition algorithms you're looking for, and then cross filter to visualize so you can really get in deep and make sure your clusters are what you think they are.
Is there any resource you can share with us, Taryn, or is that internal?
Oh, no, this is all for, yeah, I actually am working on relaunching our community notebooks. So I'm gonna hit up Mike for some of this soon, but yeah, I can send you a link right now, actually.
Cool, thank you.
Also,
while that question's in, just sidebar, we have a project coming up where we've encouraged the client to get a bunch of Tesla cores and NVLink the crap out of them. Is there like a tight workflow? Because I think what Mike was pointing out is that right now in the community, there's, especially if you're in the cloud, like a reason to kind of bounce between GPU and CPU processing, depending on need and depending on algorithm. Like, is there like a tight workflow from pre-processing all the way through publish in your mind where you can kind of keep everything on GPU? Because we're going to get beat to crap if we have to jump out of this like NVLink Tesla situation and back into basically like a hypervisor, situation where we lose all that network model.
It's getting better all the time. Like one example where you have to incur that penalty right now is in in hyperparameter tuning. And that's because it turns out, distributed GPU computing is hard. Nobody's done the work and it's down in the loop CUDA layer with MPI in order to handle the message passing back and forth between the different folds as you're tuning the hyperparameters. That work hasn't been done yet. So what you have to do today is you have to drop back into CPUs to do your K-folds. So you're constantly shuffling data onto and out of the GPU, and you're incurring that penalty that you're talking about. So in that case, you still have to do that, but it's only a matter of time before we get that sorted out in the ecosystem. There are other examples too, I'm sure.
Yeah, I mean, that I flagged before that we're looking for a data scientist ML person who's worked in a cleared position before. Like that's the kind of, so I'll just, for the community, this is the problem that much of the military and cleared situation are facing, right? Is they can define what they want to do in a data center, but they're really limited from a cloud standpoint, and they have money. So if you tell them like build a big like CUDA cluster, they're like, sure, where do you want it? But then what happens is they don't get great model performance when they're running these kind of situations, and they have a lot of distributed edge cases, which that's a whole separate conversation. Maybe we can have it another day. The point being, if you could solve all the problem set, or at least major segments of the problem set, especially around like trains to deploy or pre-training to evaluation, all in GPU, like you could do some crazy stuff in that world, right? Of sort of the IC and the DoD, because that's their world, right? Like they're very limited in terms of a lot of times compute and different things like that. But again, they have the money to sort of get a good GPU box. But they're often underwhelmed by the performance. I mean, we've been working a fair bit with the JAIC, which is the folks that are trying to do AI for DoD. And yeah, they're not seeing the performance they'd like, right? They're a whole separate conversation. But yeah, it's part of this,
That's a hard problem, because those guys, they have their own secret sauce that they're working on. They don't.
Yeah, it all has to be firewalled. Yeah.
Yeah, so it's all wired off. They don't have access to the internet. They're bringing in the libraries, and that's a whole nother challenge too. And working in a financial institution, we have similar situations. But it's really hard. The trick there is, getting stuff up and running wherever your development environment is, starting to replicate those workloads or develop those workloads, and test out all these different edge cases. You're going to find sharp edges, but the next piece is to not get discouraged. But to understand what you're tripping over, and come up with an MRE, open an issue. If you can contribute, awesome, do that, and help close the gap there. Like that's the critical piece that even in the financial sector, it's hard to get folks to do, because like in the DoD, they're walled off and they don't know what they can and can't do, what can they put on public GitHub. So then it becomes education on how to work in the open source while you're in this walled off place in a responsible way, right? That's responsible from your institution perspective.
Yeah. Well, I mean, that's what our organization is doing with the Air Force right now. They're very interested in open source. They're very committed in the Air Force to contributing back, but also consuming from open source. But to your point, I mean, they still have the same firewall constraints that a lot of the financial and fintech world does, and then maybe even kind of a step beyond, to where the comfort right now is really being completely air gapped, right? Like we start getting into like condas and package management and stuff, because they don't even want to be consuming things directly from open source. They want to be one layer removed. But as they solve problems, I mean, there is a willingness to contribute back.
Yep. And it doesn't have to be a PR. It can just be an issue with an MRE. That is gold. That is absolute gold. And it takes it. I've worked multi-days to get an MRE before.
Yeah. I hear, man. Torian, you dropped some good stuff, man. I want to let you talk about it.
Oh, I was just gonna send links, and I'm looking. We actually just did. There's a Medium post that does have a new ML workflow. So I'm gonna find that and send it to you. But basically, this isn't live yet, isn't launched yet. It's just kind of we moved over Notebooks Contrib to an external repo out of our organization. So allowing users, to community members, to kind of contribute and build out their own notebooks library outside of the Rapids repos themselves. And yeah, there's some end-to-end workflows here. That's part of the reason why I'm so interested in what Mike is talking about, because I would love to start to, one, have those kinds of notebooks, but two, then also like play, or, you know, use this to try and see like, you know, what I can do with it and make some guides on it as well. So this is going to be really cool.
Awesome. I'm glad you got that out, because it's not a new idea, right? Like I showed, this is, I'm just ripping off DaskML and QML.
Well, it's a fun idea. I like it.